Thanks, Peter. Thanks to the organizer for the invitation. Yeah, so some of you may have seen some of this before, the organizer especially, but I think it'll be new for most people. Is there a remote or anything? Okay.
There was.
Yeah.
No more.
It's
Equity order. All right, yeah,
all right, yeah, go around that. Okay. So today I'm going to talk a little bit about sort of reverse math you've been seeing over the last week or so, but how it sort of arises in the context of algebra, commutative algebra, and ring theory in particular. So, start with some, if you ever see me give a talk in the last 10 years, this is usually the first slide. So, a computable ring, which is what we're going to be dealing with today. A computable ring is just a computable subset of natural numbers equipped with the ring operations, some addition and multiplication, computable operations on the ring. And in the context of this talk, all the rings are going to have 0 and 1 element. So that's just, standard boilerplate. And for us, in the context of this talk, I don't think it's going to be an issue for this audience. It does come up once in a while, but all the rings that I'm going to consider today are going to be countable, commutative, and have an identity element. That's just standard. All right. So for a little bit of commutative algebra refresher, so I want to consider R to be a ring containing a couple of ideals P and Q. Recall that the sum of two ideals is the sum of the elements of the corresponding ideals, and that turns out to always be an ideal. If you start with ideals, you can generate another ideal that way. Recall that an ideal is prime if whenever the product of two ring elements are in the ideal, one of those elements individually has to be in the ideal. And also recall that a ring is Noetherian if it satisfies the ascending chain condition on its ideals. In other words, every infinite ascending chain of ideals eventually stabilizes. There is some review there. Finally, this is a definition you might not have seen before. You've probably seen it a long time ago. So P here is a minimal prime ideal if it does not properly contain any prime ideal. All right. And the only significant thing about this definition is that in the context of minimal prime ideals, 0 counts. So you're allowed to be 0 if you're a minimal prime ideal. So if you have a ring whose minimal prime ideal is the 0 ideal, that means that you're in an integral domain. Okay, the main theorem that we're going to sort of be considering today, some versions of it, is what I'm calling the primary decomposition lemma. And this is a theorem that you can find in commutative algebra textbooks. It doesn't have a name like this, but you can find this theorem. This theorem essentially goes back to Noether's paper, 1921, 22, something like that. Basically, this theorem is very much related to Noetherian rings, and the reason why we call them Noetherian. And basically, it says that if you're in a Noetherian ring, then you only have finitely many minimal prime ideals. All right. In the context of reverse mathematics, computability theory, it's often more useful to restate theorems about Noetherian rings in terms of their contrapositive. So rather than saying, so lots of theorems in commutative algebra say, if you're in a Noetherian ring, then you satisfy some property. In the computability context, it often it's often easier to consider the contrapositive, which says if you're in a ring that doesn't satisfy a certain property, then the ring cannot be Noetherian. So here, if your ring has infinitely many minimal prime ideals, then it's not Noetherian. So this is what I'm going to call the primary decomposition lemma in the context of this talk. All right, so let's prove this thing. The proof is it's actually not that hard to prove that. So assume that you're in a ring with infinitely many distinct minimal primes. We need to construct an infinite strictly ascending chain of ideals in this ring. So how are we going to construct this chain? Well, we're just going to do it one generator at a time, basically. All right, so you start with zero, just start with the zero ideal. Well, what are we assuming about a ring? A ring has infinitely many minimal prime ideals. I mentioned earlier that zero counts as a potential minimal prime ideal, but since our ring has infinitely many of these things, zero can't be a minimal prime. So this zero ideal, it can't be prime, which means that it violates the definition of primeness, which means that there are two elements, say A1 and B1, neither of which is in the zero ideal, which I'm calling I0 here, but whose product is there. Now, since we have infinitely many minimal prime ideals, and those prime ideals contain the zero, it follows that for one of these two elements, it is contained in infinitely many minimal primes. And so that's the element we add to I0, which is a zero ideal, to get the next ideal I1. And so you add the element that is contained in infinitely many of the minimal primes to generate the next one. And that's basically the way that the construction works. That general, that sort of schema or paradigm, you can keep repeating it to construct a sequence of generators here, such that the next generators are not contained in the span of the previous ones. And that's how you get your infinite strictly ascending chain of ideals, assuming that you have infinitely many minimal primes. All right, this strategy, this sort of scheme here, it uses the double jump. If you wanted to do this uniformly, you would need to use something like the double jump here. Right? Because the double jump tells you which of these elements, A or B, is contained in infinitely many of your minimal prime ideals. Any questions? Or all right, so that was a quick review of algebra. Now let's get more into the combinatorics. Right, the reverse math. Okay, so I'm assuming most of you are familiar with this, given all that's gone on in the last week or so. So in reverse mathematics, especially in the reverse math of algebra, these big five subsystems of second order arithmetic, they come up quite a bit. So you start with RCA, and then a little bit stronger than RCA is WKL naught, Conidis lemma. This is something that comes up quite a bit in algebra that you maybe not have thought about that much in the last week or so. Then arithmetic comprehension, that one also comes up quite a bit in the context of commutative algebra. And then finally, you have ATR I1 comprehension. Those ones do not come up so much in the context of commutative algebra. So let's say Noetherian rings. So in the context of this topic, we're going to mainly be focusing on the first three, or subsystems below ACA, basically. some other ones that I just kind of want to mention, these are maybe more relevant to what you've been thinking about over the last week or so. ADS is the ascending descending chain principle that just says if you have an infinite linear order, then it has either an infinite strictly ascending chain or an infinite descending chain. 2MLR, which is the existence of two random sets. All right, and this is like saying certain sets of certain complexity of measure 1 are non-empty. That's 2MLR. The cohesive set principle, which you've probably seen, and the atomic model theorem also comes into this. Every atomic theory has an atomic model. These are all subsystems that are relevant to what I'm going to say today. Probably the two most relevant are the first two. The ascending chain, the ascending descending chain principle, and the 2MLR, the existence of two rings. Okay, now for the combinatorics. All right, so the main sort of combinatorial structures we're going to be working with are trees, sort of infinite binary branching trees, but the sort of trees that I'm going to be considering are completely branching. So what I mean by completely branching is that typically in a binary branching tree, you're allowed to branch, twice, have 2 children, or 1 child, or 0 children, in which case you're a leaf. In these completely branching trees, either you have 2 children above you, or you are a leaf. You're not allowed to only extend by a single node. You either have to branch, have 2 children above you, or else you're a terminal node. All right, and it's a fairly straightforward theorem. You can try proving it. You can try proving it maybe in your head, but every infinite completely branching. So here I'm taking these trees to be computably enumerable. It actually, so computable trees of this sort that either branch twice or don't branch at all, those trees are not that interesting. But if you allow for computably enumerable, where from a computable point of view, you have a node, and then either at some point in the future it splits into 2, or else it never splits. But that decision is not decidable, and it's not uniformly decidable whether or not the given node splits or not. These trees are a bit more interesting computationally. Sort of add that little bit of complexity where you don't know in advance if a node's going to split or not. Those turn out to be more interesting computationally. But every infinite completely branching computably enumerable tree contains an infinite antichain. And there's a few proofs of this. One proof is that if you have an infinite tree, then your infinite tree has an infinite path through it. But so if you think about your infinite path through your infinite tree, because your tree is completely branching, along your infinite path, you must have, so if you have an infinite path like this through your infinite tree, along your infinite path, because your tree is completely branching, along your infinite path, you must have these other nodes sticking out, right? These pairs, these sort of partner nodes. We must have these nodes. These nodes, the nodes that I'm drawing, they form the infinite antichain that's asserted in the conclusion of the theorem there. So the proof, there's a proof that's very straightforward. Okay, you could make an equivalent version of this as every infinite tree with no terminal nodes and infinitely many splittings has an infinite anti-chain. So if you like to work with sort of computable trees, you know, if you don't like the computably enumerable here, you can work with sort of computable trees with no terminal nodes. And infinitely many splittings. And it turns out that these are equivalent over RCA. Okay, some facts about the tree anti-chain theorem. It follows from both 2MLR and ADS. So there's a sort of a probabilistic randomness theoretic proof of this thing. It actually involves 2 DNR. It involves diagonally non-recursive functions, which you get from 2MLR, this randomness theoretic notion, and the ascending descending chain principle. Follows from each of those individually. It turns out that its syntactic form is something called, you know, it satisfies a certain syntax that's called restricted pylon 2. And I believe, if my memory serves me correctly, this, you know, the theorem of Hirschfeld, Shor, and Slayman says that it's that because it has this syntactic form, it's going to be B sigma 2 conservative, I believe. So it has a certain nice syntactic form. Finally, you can show that it doesn't follow from Koenig's lemma. And because of sort of these 3 facts, especially the first one and the third one, this tree anti-chain theorem, it's not equivalent to any other known subsystem of second order arithmetic. Right, so in terms of that zoo picture that Richard was talking about yesterday in his talk, this is something. This is a sort of unique contribution to Demir's zoo. Okay. Now, for the rest of the talk, I want to characterize this tree anti-chain theorem that exerts the existence of anti-chains in these infinite completely branching trees. I want to sort of give an algebraic characterization of the tree anti-chain theorem, sort of a ring theoretic characterization of that principle. Okay, to do so, so the way I'm going to do it is by the primary decomposition lemma, but I want to create some versions of the primary decomposition lemma, that algebraic theorem that I mentioned at the very beginning. I want to sort of restrict that theorem a little bit. So I need a couple of definitions. So just recall, this is sort of standard algebra stuff. Recall that 2 ideals are said to be co-prime if their sum is the entire ring. So in other words, if they generate the unit in the ring, the identity element in the ring. Another definition, this definition is going to be more relevant for the characterization we're going to give. We say that 2 ideals are uniformly co-prime if for all x in the intersection, so we say that 2 ideals ij are uniformly co-prime if for all x in their intersection there exists a y in the first ideal I and a z in the second ideal j, and a, b, and r, these are a and b are just the coefficients you need to generate the unit 1. But the idea is that sort of y and z, they witness the fact that x is in the intersection, because the product of y and z is equal to x, and also, there is a linear combination of y and z that generates the unit one. And so the important thing in this definition is that it's the same y and z here and here. And that's why I'm calling it uniformly co-prime, basically, because it's the same y and z. All right, a couple of theorems here. These are consequences of that algebraic theorem I was talking about earlier, the primary decomposition lemma. I'll call them theorem A and theorem B. Theorem A, so each of these are restrictions of the primary decomposition lemma, so weakenings of the primary decomposition lemma. Theorem A says if R has infinitely many co-prime minimal prime ideals, so not only do you need infinitely many minimal primes in a ring, but they each have to be co-prime with each other, then R is not Noetherian. And theorem B says if R has infinitely many uniformly co-prime minimal prime ideals, then R is not Noetherian. So these are weakenings of the primary decomposition lemma, where we require that that the infinitely many minimal primes, we have the additional assumption that they are at a co-prime or uniformly co-prime. All right, and it turns out that over B sigma 2, RC naught plus B sigma 2, theorem B is equivalent to this tree anti-chain, this sort of combinatorial tree anti-chain theorem. So the theorem B is sort of an algebraic reformulation of this tree anti-chain theorem over B sigma 2. I conjecture that theorem A also has this property, but it's a bit it's not as obvious for theorem A. Just put it that. Remember, theorem B talks about uniform co-primeness, whereas theorem A just has general co-primeness. All right, so let's sketch. Let's sketch some proofs here. So how does the tree anti-chain theorem imply theorem B? So remember, theorem B says that if you have a ring that has infinitely many uniformly co-prime minimal primes, then your ring is not Noetherian. So there is an infinite strictly ascending chain. And so in order to show that the tree anti-chain theorem applies this thing, we start with a ring that has infinitely many minimal primes that are uniformly co-prime, and then we seek to construct a tree that sort of models some of the behavior of this ring, or sort of a relevant tree that models some of the behavior of this ring, and such that anti-chains in this tree correspond to infinite ascending chains in the ring. Okay, so every node in our tree is going to correspond to some kind of zero divisor in the ring. And the way that it's going to work is, so whenever you have a set S, so the important thing in the second bullet point is the set capital S. Whenever you have a set S that covers the entire Cantor space, then the product of ring elements corresponding to that covering, that's going to be 0, right? So these X's are indeterminants, and they are indexed by the nodes of the tree. Paths in the tree correspond to annihilator ideals in the ring. That basically comes from the previous bullet point where if you cover, then the product is equal to 0. What ends up happening is that maximal paths correspond to maximal annihilator ideals. And it's a well-known fact in algebra that if you're a maximal annihilator ideal, you're a minimal prime ideal. That's a theorem you can find in commutative algebra textbooks. If you're a maximal annihilator ideal, then you're automatically a minimal prime. If you have these properties, then it turns out that, so if you have these properties, so the way it works is that you start with a ring, you use your ring to generate an infinite, completely branching tree. This now the question is, why do antichains in the tree correspond to sort of infinite, strictly ascending chains in the ring, right? So remember that the ring indeterminants are indexed by, so we have like sigma in the tree, and in the ring we have x of sigma. So if you have an infinite antichain in the tree like this, right? If we take like, let's see. If we take like this node, and this node, and this node, and this node, something like that. If we multiply, so if we start multiplying the indeterminants corresponding to these nodes together, one after the other. So if we start with say sigma 1, 2, 3, sigma 4, we start multiplying the corresponding indeterminants together. So we have x of sigma 1, x of sigma 1, x sigma 2, x sigma 1, x sigma 2, x sigma 3, x sigma 1, x sigma 2, x sigma 3, x sigma 4. You start multiplying these things together. Then if we start considering the annihilator ideals of these products, okay, it turns out that the bigger your product is, the bigger its annihilator is, right? And so the first thing I want to sort of point out here is because we have an infinite antichain, the sigmas that we use here, they will never fully cover Cantor space. They will never fully cover the entire Cantor space, and therefore, one thing maybe I forgot to mention is that in the second bullet point there, I'd say that the product is 0 whenever you cover 2 to the n. That should be an if and only if. And so the product's going to be 0 if and only if you cover all of Cantor space. Because we have an infinite antichain here, the products that I'm considering here, the product will never hit 0. It will never hit 0 because we have an infinite antichain. And not only that, but it's a property of the construction here, these annihilators will strictly grow and grow. right? And that's basically because of the second bullet point there, that the product is 0 whenever you cover to the end. That may be a little bit opaque, but it's true. Okay. And so the annihilator ideals you get from an infinite antichain, that gives you an infinite strictly ascending chain in the ring that you started with, the ring with sort of infinitely many minimal prime ideals that are uniformly co-prime. This is basically the main idea of the construction here. All right. Let me know if you have any questions, right? So the other direction is that theorem B implies this tree anti-chain theorem. And for that, so given a computably enumerable complete branching tree, we need to construct a ring that sort of models the behavior of this tree. And this construction is maybe a bit easier to follow. So what I want to do is, I start with the tree. I want to build a ring whose primes, whose minimal primes, sort of model the tree in a nice way. So the way that this construction goes is we have the tree to start with. We are building the ring in this case. So we have the tree. So we start with the root. We have a tree like this. Okay. So the way it works is, so now we're building the ring here. So I'm creating this indeterminate here. The indeterminate corresponding to the root of the tree, we just make 0. And then we have this rule that says, so every node here gets an indeterminate. Right, so the node sigma, we have the corresponding determinant x sub sigma. And the rule is what you would expect, especially in the context of prime ideals, is that the indeterminants corresponding to the two children that you may or may not have, but if you have two children, then the indeterminants corresponding to your two children, they multiply to you. What does this mean in the context of prime ideals? This means that every prime ideal must climb the tree, right? And so if you think about it a little bit, but minimal prime ideals of this tree are going to correspond to maximal paths. You know, so these two first bullet points, these two first bullet points, they give you the fact that when you multiply a covering of two to if you multiply together the indeterminants corresponding to a covering of Cantor space, you get 0 if you take the first two bullet points together. That's something I should say. That was a property we had in the previous construction. Finally, what you want is you want inverses for all polynomials in this ring such that the intersection of all the partial coverings yielded by the monomials is empty. What this basically means is that the greatest common divisor of the monomials of this polynomial, that greatest common divisor is equal to 1. And so the monomials do not share a common factor. That's what I'm trying to say here. So for the polynomials whose monomials do not share a common factor across all the monomials, we want to invert those. We want to create inverses for all of those. And it turns out that this is a well-defined operation, because polynomials whose monomials don't share a common factor, that's a multiplicative subset of a ring. So if you have two polynomials who don't share a common factor, you multiply them together, you're also going to get something that doesn't share a common factor. Okay. Okay. Any questions? Any questions? All right. The nice thing about this last property here is that it turns the ring into a principal ideal ring. So I claim that every ideal is actually principal in this ring. It's actually generated by a monomial. So, every element of this ring here, the ring that I've described here, every element, it's a unit times a monomial. Because if I give you a polynomial in the ring, if you factor out the greatest common divisor of all the monomial summands, then what you're left with is the greatest common divisor, the greatest common monomial divisor of all the monomial summands. You divide that, you factor that thing out, and what's left is a unit by the third bullet point. So every polynomial reduces to a monomial times a unit, basically by this third bullet point. What that gives you is that gives you a principal ideal ring. Every ideal is generated by some monomial element of it. So this gives you a nice ring. So sort of localizing this way, it gives you a ring with a nice structure that you can code things into. And so now, if so in the context of theorem B, once you've created this ring, it turns out that if you have a strictly ascending chain of ideals in this ring, one can effectively, the effectiveness might not be totally obvious, but it's true. One can effectively find a principal generator for each of those ideals in the chain. And then you need to use a little bit of B sigma 2 here. This is where B sigma 2 is relevant. You need the infinite pigeonhole principle. Along with the sequence of exponents. So the way the coding goes here, the sort of relevant thing is the sequence of exponents in these monomial generators. That's what's going to code. That's what's going to essentially code the antichain. The sequence of exponents basically codes the antichain of T. Right, and that may be a little bit opaque, but it's true. Okay, so over RCA naught, what I showed, what I sort of sketched, is that the tree antichain theorem implies theorem B. The converse you need a little bit of B sigma 2. You need the infinite pigeonhole principle in the sort of group that I sketched. We create other sorts of tree anti-chain principles that are relevant, sort of form of gradation, possibly. I don't know if it's strict or anything. But for each natural number n, we can let n TAC, sort of the nth tree anti-chain theorem, be the principle that says for every infinite tree with infinitely many splittings, there is a path non-increasing. So as you go up the tree along a path, you're not allowed to increase. You can either stay the same or decrease along a path such that, so in the first bullet point here, this n is the same as the n up there. So you start, so for n TAC, at the root, you start with n, and then as you go up the tree, your function can either stay the same at n or it can decrease. But the second bullet point says your function has to decrease along paths sort of infinitely many times, infinitely often. There have to be infinitely many strict decreases along a path. You start at n at the root. Now, it turns out that the tree anti-chain theorem is just equivalent to 1 TAC, okay? So 1 TAC, you have to start at 1, and then along paths, you have to drop to 0 sort of infinitely often, and the places where you drop to 0, those must form an anti-chain. So the tree anti-chain theorem, that's just equivalent to 1 TAC. And we'll call WTAC, NTAC without the n. This is a little bit vague, but what I mean here is there exists a natural number n. What I want to say here is that yes, sorry, there exists an actual number n for every infinite tree. There exists an actual number n. Okay, and it turns out that over RCA naught, we have that the tree anti-chain theorem implies theorem B. Remember, theorem B is the primary decomposition lemma with the infinitely many uniform coprime minimal prime ideals. The theorem B is an algebraic theorem. That implies theorem B implies WTAC over RCA naught. So all that's true over RCA naught. Over RCA naught plus B sigma 2, you get equivalences. Scratch this A. That A shouldn't be there. But you get equivalences between the tree anti-chain theorem, theorem B, and WTAC if you have B sigma 2. You know, I'm not sure if the B sigma 2 is necessary. Now I'll sort of wrap up. I'll wrap up with a little bit about the primary decomposition lemma, which is that it's the general algebraic theorem that Noether was talking about in her 1922 paper. So this is the theorem where your minimal primes, they don't necessarily have to be coprime or uniformly coprime. This is the theorem that appears in your commutative algebra textbook, basically. So in order to analyze the primary decomposition lemma, we need to use infinite combinatorial structures that contain cycles, that contain these undirected cycles. So the reason why I have to assume co-prime in order to model my ring, model my trees by rings, and model my rings by trees, I need the co-primeness because basically whenever I have a splitting in my tree, it's because something happens, something corresponding happens in the ring. I have two generators that sort of multiply to give something that's in the current ideal, but none of whose generators are. The reason why I need the co-primeness is because in order to model this as a tree, I need to be sure that these two, like A and B, that multiply to C, I need to be sure that there isn't some other minimal prime ideal containing both A and B, right? Because that might happen. So you might have A, B, and then, some other prime here, some other minimal prime. And so in general, when you're considering the general primary decomposition lemma, and you try to sort of model it combinatorially this way, you need to consider sort of graphs that have cycles in them. However, if you know that A and B are somehow co-prime or uniformly co-prime, then once you create a splitting, so once you have these two elements, you know that because of the co-primeness, you know that there could never be a prime up here containing both of them. So in general, you need to consider these combinatorial structures that can have cycles. So more general means trees. So in general, using sort of the same kind of logic, with the primary decomposition lemma, this is the thing that Nither was talking about 100 years ago. This follows from the chain anti-chain principle and WKL. So in the context of algebra, so we need WKL in this context to construct our ideal. So WKL is sort of the weakest principle in which you can sort of construct ideals. The way we got away without using WKL in previous slides, and I haven't really talked that much about WKL so far. The reason we got away without using WKL in previous slides is because the ideals I was considering were all annihilator ideals. And it turns out that so annihilator ideals are always computable. And so that's the reason why we got away without WKL in the previous slides. So you need the chain anti-chain theorem here because you need to consider these sort of graph structures that possibly have cycles in them. And then you also need WKL because in the chain anti-chain theorem, if you get back an anti-chain, you're good and you can use annihilator ideals. But if you get back a chain, then you need, turns out you need WKL to build your ideals for you in general. Like I don't know if the WKL is absolutely necessary, but I couldn't think of a way to get rid of the WKL. If you get back a chain, you might need WKL to build the ideals for you. You can't simply rely on annihilator ideals if the chain anti-chain theorem gives you back a chain. All right, I'll just finish with a couple of questions. Well, these are the things I'm sort of thinking about right now. The second one I kind of touched on. Do we have pi/1 conservativity for the tree anti-chain theorem or the primary decomposition lemma? So I'm thinking about that a little bit. And then does the primary decomposition lemma, which we need to sort of more general combinatorial structures with cycles in them, does that follow from some sort of measure theoretical principle like randomness? So the tree anti-chain theorem, so the trees where we don't have cycles. I mentioned earlier that follows, that a tree principle follows from the existence of two random sets. Basically does the primary decomposition lemma, which is Noether's theorem, Noether's result from 100 years ago, the more general thing, does that follow from some kind of measure theoretic principle? What's the solution? Does the solution set always have a measure 1, basically? Does it follow from n randomness or some n? Say, yeah. All right.